Okay, cool. All right. So folks, I'm going to go ahead and start sharing my screen so we can take a look at some questions from WebAssign. So if you have some questions that you'd really like answered from WebAssign, maybe start making a quick list of that, and then we'll just start going through some questions, okay? All right. So, what kind of questions do we have on WebAssign? Or would folks like me to pick?
I have a question on number 70.
Number 70. Okay, yeah, let's do it. All right. Okay, so number 70, you should have an X in the front, yeah? And then what are your numbers on the inside?
4x plus 7.
And is that raised to the 8th power?
Yeah.
All right. So let's take a look at this question. So what are folks' strategies? Anybody have a strategy that they want to share for this? Okay. I think most of us would maybe think, oh, maybe U sub would work. And I'm betting that most of us who thought U sub wanted to make the inside thing, like the thing raised to the 8th power as the U. And that would actually be a great way to start. So we're going to let U equals 4x plus 7, okay? And that's going to make du equal to 4 dx. Now, what we're going to do is I'm going to substitute out here real quick, and let's just see what we still have left, all right? So when I substitute at this phase, I have the integral. I should probably divide that 1/4 away, or the 4. I end up with x, so that didn't get substituted yet. I get u to the 8th, and then I get 1/4 du. Does that sort of make sense as a first step?
Yes. Yep.
Okay. So this kind of question, I'm not going to ask this on the test, but I think it's important that we see it because this does kind of start to come up more frequently in Calc 2, okay? So this particular type of U substitution, I will not ask on Thursday's test. However, it's a good one to kind of see. The reason why I'm not going to ask something like this on Thursday's test is because this actually requires you to do sort of like a second substitution. And so here's what we're going to do. We're going to take the u that we have, and we're going to isolate x. And the reason why I'm going to isolate x is because I notice I still have just an x in there. And I need to get rid of that because everything else is in terms of u. So if I solve for x in the thing that's highlighted in the pink, I'm going to do u and then minus 7, and then that would equal 4x. And then I'm going to go ahead and divide by 4, so I get u minus 7 over 4. So what we can do now is everywhere I see the x, I can replace it with u minus 7 over 4. So let's see what happens when we make this additional substitution. I get the integral of u minus 7 over 4 times u to the 8th times 1/4 du. And I'm going to go ahead and pull out the two constants that I see. And so to me, those two constants, I have like this 1/4 here, and then I have like another 1/4 because this 4 is on the bottom. And so when I bring those both out to the front, I'm going to get 1/4 times 1/4, or 1/16. Now what I have left inside is u minus 7, because that was all the numerator of that 4, times u to the 8th du. Now, what's really nice about this is I can go ahead and distribute that u to the 8th to the first term as well as that second term. So let's see what that gets us. We have our 1/16 in the front. Now we have the integral of u to the 9th minus 7u to the 8th du. And now I'm at a place where I can use the power rule. So this will give me 1/16. The power rule for u to the 9th is going to be u to the 10th, because I added power, and then I do the reciprocal of that, which is 1/10, minus 7 times 1/9 u to the 9th. And then I can clean this up a little bit. So 1/16 times u to the 10th over 10 minus 7u to the 9th over 9. And let me just take a peek at how WebAssign answers this. So they do combine the denominator. So they're going to distribute this 1/16 to the first term as well as the second term. So you're going to get u to the 10th over 160 minus 7u to the 9th over, where's my calculator, 16 times 9, which is 144. And we're not going to forget our plus capital C, because this is an indefinite integral. Now, the last thing we need to do is everywhere we see the u, we need to replace that with the 4x plus 7. So we can get our answer back in terms of x. So I'm going to have 4x plus 7 to the 10th over 160 minus 7 4x plus 7 to the 9th over 144 plus a capital C. All right. So what makes that tricky is you make your u sub, you pick your u the same way you pick your u in any other case. However, then you kind of have to go back and rearrange some stuff so that you can sub out that additional x that's left over. Okay. And again, this kind of u sub will not be on the exam, but it is something you should expect when you get to Calc 2. All right, does that answer questions about number 70?
Yeah, thank you.
All right, cool. What other questions did folks have? Again, I'm happy to pick, but I know that you have a deadline for your homework, and I want to support you around finishing that in a way that feels good for you. All right. There was one question, let me find it real quick, that someone had asked me, and I know someone else had asked me too, and Danny also brought it up. So I just want to make sure that we feel sort of confident on answering that kind of question. But again, hold on, let me figure out where it is first.
After that, could you try 74?
Yeah, we can definitely do 74.
Okay, thank you.
Okay. I can't find that problem right now, but I will go back in and find it. So 74 for right now. This one looks like it's not randomized, so everyone should have the same 74. And the way they write it is the integral of dx over x natural log x squared. Okay, so I would rewrite this a little bit in a way that looks friendlier to me. So I don't really like when the dx is on the top. I kind of like to move it to the end just so I can see like what is the actual thing I'm taking the integral of. So when I do that, I get the integral of 1 over x times natural log x is squared on the bottom, and then I have the dx next to that. Now, if I wanted to, I could even split this so it says something like the integral of 1 over x times 1 over natural log x squared dx. And the reason I can split it like that is because when I'm multiplying fractions, I multiply top times top, and then I multiply bottom times bottom. And so what I'm going to do here is I'm going to identify a u that I need. And again, u tends to be the thing raised to the power, or in the case of exponents, it is the thing in the power. So in this case, a good choice for u might be this natural log of x, because the natural log of x is squared. So I'm going to let u equals natural log of x. And that makes my du 1 over x dx. Now, what's really nice about this is because I split my fractions, I can see very clearly that the thing in the pink is going to become u. So u squared on the bottom. However, 1 over x dx is going to be replaced with du. So everything in the green just becomes du. And then here's what we have left. So I have the integral of 1 over u squared. That was the thing in the pink. And then the 1 over x dx just becomes du. So in order to find this antiderivative, I'm going to go ahead and rewrite it so I can see the power, u to the negative 2. And then I'm going to apply my power rule, which is going to be 1 over the power plus 1, u to the power plus 1, plus c. And then I'm going to clean up my fraction in the front and my power, and then I'm going to put back in my natural log of x. So this is going to be negative 1 over 1, u to the negative 1 plus c. Or I could say this is negative 1 over u plus c. And I'm going to say that's negative 1 over natural log x plus a capital C. All right, Alexis, does that help with that question?
Yeah, I split it up differently in the beginning. That's why I got stuck.
Oh, how did you split it up?
Well, I didn't really split it up. That's the thing.
Oh, okay.
Yeah,
And I find that sometimes like rewriting it like this, especially when there are fractions involved, just makes me feel a little bit more confident that I know what I'm going to be subbing out.
Okay.
Okay.
Yeah, thank you.
Okay. So I did find the question that I know at least a few people had questions on, and maybe I'll do that one right now. And if you have a question, just kind of hold that and I'll be ready to answer your question after we do this one, okay? So the one that I noticed that a bunch of people maybe had some questions on is number 26. So is there anybody who's in the lesson right now who had a question on number 26? Because I'm happy to use your numbers.
Could we use mine?
Sure. All right, what are your numbers?
Okay. It was 0 and -4 on the integral.
So -4 on the bottom.
And then 0.
Okay.
And then 5 plus the square root of 16 minus x squared.
Okay. Perfect.
Yes, yeah.
Okay. Ah, I got to the end of the page. Okay. All right. So this one, we're going to kind of do this in a progression to create the diagram, okay? So let's take a look at what this might look like. So one part of this that I want us to know is this part, that square root of something squared minus x squared, okay? That is something that I want us to be able to recognize is going to be a semicircle. All right, so it's gonna be the top half of a circle. But if I had a minus sign in front of that, then it would be the bottom half of the circle. Okay. And so let's go ahead and draw just what that semicircle would look like. So if I draw that semicircle, Diana, are you so proud of my diagrams now?
So proud. Those lines are super straight.
All right, so if I see 16 minus x squared, in my head, I'm thinking 4 squared minus x squared. And the reason I'm thinking 4 squared is because that's going to be the radius of my circle. So the square root of 16 minus x squared is going to have a radius of 4. And it's going to look something kind of like this. Okay, so that's just this part. That does not have the plus 5 with it yet. So in order to take care of that plus 5, those of you who had me last semester maybe remember that that plus 5 means you're going to take your graph and you're going to move everything up 5 units. So this part right here, we can say is a vertical shift up 5. So I'm going to take the circle that I have, or the semicircle rather, and I'm just going to move every single point up 5 units. Okay. So if I move it up 5, that means that this point is not at -4, 0, but it's going to be at -4, 5. So 1, 2, 3, 4, 1, 2, 3, 4, 5. And then this point isn't going to be 4, 0. It's going to be 4, 5, because I move everything up 5. So 1, 2, 3, 4, and up to 5. Okay, and that also means that this point up here is not going to be 4, 0, but it's going to be 9, 0, or sorry, 0, 9. So 5, 6, 7, 8, 9. So my semicircle gets shifted up to like here. And then I have underneath, what shape do I have underneath? Yeah, we have a rectangle now. Okay, so that plus 5 means that we're going to create a rectangle underneath our semicircle. So that's what it is visually. Now, I drew more than I needed to draw because let's take a look at my bounds. My bounds start at -4 and it stops at 0. So what that means is I only want this half of the rectangle, and I only want this half of the semicircle. So in other words, I'm going to have the area of the blue rectangle and then the area of the green quarter circle. So if we go back and find that area, let's take them piece by piece. So the semicircle, or quarter circle rather, since it's a fourth of a circle, I can write 1/4 pi r squared to get me the area. And I know that it's going to be 1/4 because it's half of the half circle. And my radius for this circle is 4, so 1/4 pi times 4 squared, which is going to give me 4 pi. So 4 pi represents the area of that quarter circle. And then if I try and find the area of that rectangle, it's just going to be base times height. And I know the base of this rectangle is 4, and the height of this rectangle is 5 because I shifted everything up 5. So 4 times 5 gives me 20, and 20 represents the area of this rectangle. And so to get your total answer, you're just going to write the green part plus the blue part. And so for this case, your answer will be 4 pi plus 20. Okay, so this one definitely helps if you know your graph transformations, because you can just slide it up 5 and then figure that out. If you feel like you can't remember, then you can always just plot a regular like XY table, pick some numbers to plug in. But I think that gets a little trickier because a few of these numbers are nice numbers, but not all of them are nice numbers. But I think it was Shannon. Shannon, does this clarify 26 for you?
Yes, thank you so much.
Okay, awesome.
I have a follow-up question for this one.
Sure. What's up?
Looking at the given information, isn't the center of the circle not at 0, 0? Wouldn't that change the area from 0 to 4? Like if you move the center?
Well, you're moving the whole thing. So you
So like
still,
if it was shifted to the left, then the portion of the curve of the, you know what I'm saying? Like if you had
yeah,
shifted this quarter circle to the left, it wouldn't have been a full quarter.
right. If we're moving things side to side, then yeah, our bounds usually move with that. But I think what we're looking at here is just more of a, like, let's just add a rectangle underneath whatever shape we want them to find and see if they can figure out that we're just adding a rectangle.
Okay.
Does that make sense?
Yeah.
Okay. All right. So what questions do folks have on the homework? Don't be shy.
Uh, 34.
34. All right. Let's take a look at 34. Okay. So 34. 34 says use part 1 of the fundamental theorem of calculus to find the derivative of the function. So we have the function capital F of x. So I know that that's an integral from x to 0 of the square root of, what numbers did you have?
2.
2 plus secant of
I'm sorry. 2.
oh, both numbers were 2?
Yeah.
Oh, okay, cool. All right, so square root of 2 plus secant 2. Okay, so if I know that I'm finding the derivative, that means I'm taking the derivative of an integral. And so what that means is whatever my thing is that I'm integrating, okay, my answer will be some form of, we call this the integrand. So the thing that's being integrated. So some form of the integrand. So in my answer, I should have like this square root of 2 plus secant of 2x somewhere in there, okay? And again, I know that because I'm taking the derivative of the antiderivative, which should give me my original function. So what we need to pay attention to here are the bounds. And so when we learned this in class, we talked about sort of like if one of the bounds is a constant, what happens if the x is on the top versus the x being on the bottom, okay? So just to kind of refresh your memory a little bit, if you have the integral and you have a constant and just x at the top, then all you're gonna do is replace t with x in your integral. So for example, if my bounds were switched and I had a 0 on the bottom and an x on the top, then my answer would be the square root of 2 plus secant 2x. So I would just literally replace all the t's with an x. But in some cases, we have a situation where the x is on the bottom and the constant is on the top. And in those cases, we replace t with x, all right? So we're still gonna replace our t with an x, but we're also going to change the sign. So if my integrand, or the thing in the pink, was positive, then I'm gonna make it negative. And if the thing in the integrand was negative, I'm gonna make it positive. So if I look at this one, I notice that, yeah, I have an x on the bottom and a constant on the top, or an x on the bottom and a constant on the top. So all I'm gonna do to take the derivative of the integral is I'm gonna rewrite my function, but everywhere I see a t, I'm gonna put an x. So 2 plus secant 2x. And I'm gonna change the sign of it and make it negative.
Okay.
Okay. Now, I did want to sort of highlight one more case. Let's see if we can actually find a question that does that. So the third case I want to highlight is that sometimes we have like some function of x in the bound, and then we have another function of x. And anytime we do that, we're still going to replace t with x. But what we have to remember for problems like this is we need to incorporate in chain rule to take care of the fact that the bound is not just a constant or not just x. So for example, let's say I change this question to say f of x equals the integral from x squared to 0 of 2 plus secant 2t dt, okay? So what I changed is I made that bottom bound into a function of x. So it's not just x, but it's x squared. So when I find the derivative of my antiderivative, I'm gonna have my function, but everywhere I see a t, I'm gonna put an x, so square root of 2 plus secant 2x. I have to multiply by the derivative of that function. So x squared has a derivative of 2x, so I need a 2x in the front of that. And the bound is on the bottom, like the function is on the bottom, and the constant is on the top, so I have to change the sign and make it negative. Okay, so by changing the bounds, it changes the way that we incorporate the bound into our answer. Does that clarify number 34 for folks?
Yeah, that helps. Thank you.
Okay. All right, other questions? It could be from way back when.
Can we do number 42, please?
Yes. Ooh, okay. Okay. So 42 is actually one of the topics that we may not, likely won't get a chance to cover. However, it is a little bit of an extension of stuff that we already kind of know. So I'm going to talk through this question because it is on the homework, but I will say that this kind of question will not be on the exam. Okay. It is one of those things that I knew I kind of had to cut because we lost a week of curriculum, but I wouldn't study it for the exam. Okay. So I'm going to go ahead and sketch the graph here. 10, 20, 30, 40. So 10, 20, 30, 40. 1, 2, and 3. So, all right, so 1, 2, and 3, and 1, and 2. Okay, so this one looks like it goes like, oh, something like that. Okay, so this right here is the graph of the integral. Okay, so this is the this is t, this is f of t, and this is telling us that g of x equals the area underneath this curve. Okay, so we're trying to find out where you have less area and more area. So if you think back to when we talked about graphs of derivatives and how the graphs of the derivatives told you about the slope, and so we use that to look at maybe like graphs of velocity. So this is kind of the same thing in that we kind of have a graph of velocity right now. So this is our velocity. And when we integrate velocity, we actually get position. And so when we're looking at velocity, a few things to remember is that positive y values on velocity mean that you have you are traveling to the right. So you're going to the right. Whereas negative y values means you're going to the left. And anytime the y value equals 0, then your particle is at rest. Okay. So when we look at this particular graph, part A says, at what values of x do the local minimum and maximum values of g of x occur? So they have 2 minimums and 2 maximums. So if I were just to draw like a regular graph and I said, okay, well, I am drawing this and I'm showing you that there's a minimum here. What can you tell me about the slope on the left-hand side and on the right-hand side of that point?
The left slope will be negative and the right would be positive.
Good, so negative m and positive m. Now, what that means is anytime you have a minimum, so a minimum on your original function, that means that you have a case where your velocity or your derivative goes from a negative y value, it crosses the x-axis, and it goes to a positive x value, or positive y value. So this part down here represents the minimum slope, whereas this part up here represents the positive slope. So if I'm trying to find out where x min happens, I'm looking for everywhere the graph crosses the x-axis from the negative to the positive. So the first time I see that happen is here, okay, because the graph goes from the negative y values to the positive y value. And then I see that again right here. So for part A, your answer for the x min, they want the smaller one first, that is at 15. And then they want the bigger x min, or the one further down the axis, and that should be at 35. Now, I could ask you a similar question where I say, I'm going to draw this curve, and this curve has a maximum. And if I asked you to tell me about the slope on the left and the right of this point, you could tell me this is a positive slope and that this side is a negative slope. And so a maximum on the original or on the position function, what that looks like is you go from the positive y values and then you cross down into the negative y values, because you're going from a positive slope to a negative slope. And so for the x max, the smaller one, would be like this point right here, because it goes from the positive y values to the negative y values. So that's going to be at 5. And then that actually happens one more time at here, which should be 25 if I had drawn a more accurate picture. Okay. Now, does that kind of clarify part A?
Yeah, that makes sense.
Okay. So part B says, where does G have the absolute max value? Okay. So G has a maximum value when you have the most area under the curve. Okay, so we're looking for the most area. And I know that maximum G means most area, because if I look back at this, G is the area of velocity, or the integral of the f of t. And so it does matter whether things are above or below the graph. And so if I kind of went and said, okay, this area, I don't know what it is, but it's definitely a positive value. But then when I add in this bottom bump, if I just add the top green and the bottom red, am I going to get a positive value or a negative value?
Negative.
Negative, okay. And what happens if I add back in this bump? So 2 greens and 1 red. Do we have positive or negative?
Positive.
Positive, okay. And then I add in this one, I'm probably going to get a negative. But when I add in this last bump, I'm going to get overall like the most area under the curve because I have 3 positive areas and I'm taking away 2 negative areas. So the point where G has the maximum value is actually going to be at the end. So that will be at 45. Okay. For part C, it asks you to find the regions where it is concave down. Okay. The short of this is that concave down means something kind of like this. All right. So visually, it's something that does not hold water. And we want to find out where the graph kind of looks like it's facing down, okay? But this is what it looks like on the original function. So what this looks like on the graph of the derivative is we're going to be looking for places that have negative slope of f of t. Okay, so concave down on the original means negative slope of f of t. And so if I find those regions, that's going to be, I think, from 2.5 to 10, and then from 20 to 30, and then from 40 to 45.
It's only where it's pointing downward.
Yeah, it's only where it has a negative slope on the graph of the derivative.
Okay.
Okay. All right, the last one says to sketch the graph of G. All right, so to sketch the graph of G, we're gonna actually use the ideas of sort of like the greens and the reds, okay? And we want to think about what we already found, which is the maximum and minimum. So one strategy that I would do, especially because this is like a multiple choice one, is let's find, let's see, the blue ones were the minimum. Okay, so you're gonna try and find a graph that has the bottom of bumps or the minima at 15 and 35. And then you're going to try and find this graph that also has maxima or high points at 5 and at 25. I believe there's only one graph that matches that description.
Should it look exactly like the one that they gave us at the top?
No, because you need to have the minimum at 15, and the original graph has a minimum at 10.
Professor, do we have different numbers for our graphs? Because mine is 2, 4, 6, 8, and those are really big numbers that you have. So I'm having
Yeah, it might be different numbers. This one's in blue. So I thought it was only the red ones that were different, but it could also be blue for the graphs.
Okay, cool, thanks.
But yeah, there should be like a top of a bump at 5, and then there should be a bottom of a bump at 15, and then a top of a bump at 25, and a bottom of a bump at 35. And I think based off of the choices that I see on mine, that there should only be one option that works with that. They all do kind of look like squiggles. So if that's what you mean, like, yeah, they're all going to be squiggles. It doesn't necessarily look different, but the places where it has a high point or a low point are going to be different. All right. Again, I would say that 42 is one that's not going to be on the test, but it is sort of a conceptual way to think about how derivatives and integrals relate to each other. All right. Does anyone else have other questions? Would we like to do a related rates problem?
Could we do number 40, please?
On the homework?
Yes, please.
Okay.
Thank you.
I think a related rates problem after number 40 would be helpful too.
Okay, cool. All right, so number 40. Okay, so this one looks like it's not randomized, so we should all have the same numbers, and it looks like mine is the integral from -1 to 2 of x cubed dx. Okay, so it says evaluate the integral and interpret it as a difference of areas. So one thing that we want to know, let's actually start with the visual for this, okay? So the graph that I'm looking to sketch, okay, so the graph that I'm looking to sketch, is the graph of x cubed. And so if I plot that, okay, that's one of the parent functions that's really helpful to know. But if I plot that, I'll get 0, 0 as a point, 1, 1 as a point, 2, 8. So 2, 4, 6, 8, and then -1, -1. And so if I sort of connect that, I know that I have a graph that looks like that, and then it would sort of continue down like that. So the x cubed is a good graph to know. And so when I think about what the bounds mean, this bound on the bottom, -1, means that that's where I'm going to start finding my area. So there's my starting point. And then the top bound is a 2. And that's going to be where I stop finding the area. So x value of 2. Whoop. Okay. So the area that I'm trying to find is going to be this green area down here. So it's between the curve and the x-axis, and this blue area. Okay. So when I say find the integral from -1 to 2 of x cubed dx, this is what we're finding, okay? Now, based on that, I know that the green area is below the x-axis, so that's going to count as a negative, and the blue area is above, so that's going to count as a positive. And I notice that the blue area is bigger than the green area, so I know at the end my answer should be a positive value. So that one should match with one of the graphs below. Okay, so they've provided the graph and the shading in the light blue. Now, when they say evaluate the integral, that means find the definite integral. So we're gonna take the antiderivative of x to the third. So power rule says that's x to the fourth and then 1/4. I'm gonna drop the line, put a 2 and a -1. And I'm gonna plug in 2 first, and then I'm gonna subtract what happens if I plug in 1. And so this is gonna give me 1/4 times 16 minus 1/4 times 1, or 16/4 minus 1/4, which is gonna give me 15/4. Okay.
Thank you.
You're welcome. All right, let's see if we can find a good related rates question. Okay, let's take a look at, so I just went into the exam 3 review, the optional assignment in WebAssign. And we're gonna go ahead and do the, do question number 2. So question number 2 is a ladder question. Okay, so this is 2 from the review. So we'll call it 2R. So 2R says that you have a 20-foot ladder, okay, and it's leaning against a wall. And if the top of the ladder slides down the wall at a rate of 3 feet per second, how fast in feet per second is the bottom moving along the ground when the bottom of the ladder is 10 feet from the wall? So let's go ahead and sketch a diagram. They provide one, but it's good to practice drawing what that's going to look like too for yourself, okay? So I've got sort of like the side of the building and the ground, and then the ladder is sort of something like that right now, okay? And so we can say that this is z equals 20 feet, all right? And while I'm here, I'm gonna say, let's fill in our dz dt. Like, what is the rate of the ladder changing in length?
0.
0, good. And can you explain why it's 0?
Because it's not getting any longer or shorter.
Yeah, the ladder's not getting longer or shorter. So these ladders are not like the fancy ladders where you can extend it or make it shorter or like turn it into like a 3 thing. Like, it's just a ladder. It's literally, there's no other moving parts. It's just the ladder. Okay, so that's why we can say that dz dt equals 0. And that's a good thing to remember, that anytime there's a part of the situation that's not changing, that means that the rate of its change is always going to be 0. Okay. So let's fill in our other information. They tell us that the top of the ladder is sliding down the wall, so dy dt, and it's sliding down the wall, so that's going to be a -3 feet per second. So that's another good place to kind of be aware that if distances are increasing, it's going to be positive. But if distances are decreasing, it's going to be negative. All right, we could say the same thing about like volume. If volume is increasing, it's going to have a positive rate. Excuse me, but if volume is decreasing, it's going to have a negative rate. Okay, so that's one thing to look out for, is you can write in all your numbers, but make sure that your signs are correct. All right, so I'm going to put y equals. I don't know what that is given the problem yet, so I'm just going to leave it for right now. And then what is the last piece of information they tell us? They tell us that the bottom of the ladder is 10 feet from the wall. And they want us to find how quickly that bottom is moving along the ground. Okay, so we're looking for dx dt. Well, let's go ahead and write out our equation. So I look at this and I say, nobody's asking me about any angles, so I don't need to use sine, cosine, or tangent. But they are asking me about the relationship between three sides in a presumed right triangle. So that takes us to using the Pythagorean theorem. So we've got x squared plus y squared equals z squared. And when we take that derivative, we get 2x dx dt plus 2y dy dt equals 2z dz dt. Now again, my personal preference is to divide all the 2's away. It makes my computations a little bit more streamlined for me, and it's just like less numbers to deal with. So that leaves me with an equation of x dx dt plus y dy dt equals z dz dt. And now let's plug in what we have and see if we have enough information or we need to find more information. So I know that I can write x as, whoops, not x, as 10. So 10 and dx dt. So I filled in the information I know from the horizontal. Plus, well, I don't know my y, and my dy dt is -3. And my z is 20. My z is 20, and my dz dt is 0. Okay, well, let's simplify that a little bit. I'm going to get 10 times dx dt minus 3y equals 0. So if I want to find dx dt, then I have to find y. Like, I can't have two unknowns and only one equation. So we're going to go back and we're going to find our y. Okay, and we're going to find our y using the Pythagorean theorem. So I can say that 10 squared plus y squared equals 20 squared. So I just took all three sides that I knew. So the 10 squared and the 20 squared are my x and z. And then 100 plus y squared equals 20 times 20 is 400. And so y squared equals 300, or y equals the square root of 300. And I'm going to go ahead and take out the 100. So I know the square root of 100 is a 10, and then I still have a 3 left in there. So that's what I'm going to plug in for y. So I get 10 dx dt minus 3 times 10 root 3 equals 0. So this gives me 10 dx dt equals, I'm going to distribute that 3, but also add it to the other side. So 30 root 3. And then I divide by 10. So 30 root 3 divided by 10 will give me 3 root 3. And that is my solution for how fast the ladder, the bottom of the ladder, is sliding again away from the wall. And it should be a positive number because even though the ladder's coming down the wall, it's also moving away from the wall. So that distance is getting bigger, so it's going to be positive.
Thank you. That was a good one.
Okay. Let's maybe take a look at one more. All right, let's take a look at question number 12. Okay, so we're going to do 12R, which is in the review. And if you have a question back on the regular WebAssign, don't be shy, ask it after we're finished with this. I'm happy to go back to the other assignment, okay? All right, so number 12 in the review. Number 12 in the review says that you have a vertical cylinder that is leaking water. So you've got a cylinder, all right? Well, okay, so you've got a cylinder and it has water in it, and the water is leaking out of this tank. And so it is leaking out of the tank at 1 cubic foot per second. So one of the pieces of information is that something equals 1 cubic foot per second. What would you say we could, like, what variable could we use to represent 1 cubic foot per second?
Do we use U as a variable or no?
Well, I wouldn't use U, first of all, because what I have looking at the units, I'm not looking at a distance or a volume, like I'm not looking at a singular thing. But when I look at cubic foot per second, that means that I'm looking at a rate. So U does not represent a rate. Like if I look back at example 2, like dx dt represents a rate. dy dt represents a rate. dz dt represents a rate.
Maybe like dr dt.
Okay, maybe dr dt. So R would stand for what?
Oh, never mind.
R would stand for maybe radius in this case. So, but I look and I see cubic feet, and cubic feet is usually used to describe volume, right? So based off of the units, I know that I have dv dt. Okay, so the problem doesn't say dv dt equals 1. You kind of have to intuit that from the units, okay? And I definitely find the units to be really helpful here. And those are never the numbers in red, so I would just like make sure that you look at what those units are, all right? Now, this water is leaking out of the tank. That means that this is going to be a -1 because the amount of water in the tank is decreasing over time. All right, so that was just the first sentence. The first sentence said a vertical cylinder leaking water at a rate of 1 cubic foot per second. So let's look at the next sentence. If a cylinder has a height of 19 feet, okay, and a radius of 4 feet, at what rate is the height of the water changing? So they say that the height of the water is changing, and they want us to find out what that is. but the exact moment, like we're not looking at the starting time, like when the tank was full, but they actually want us to find out how quickly that height is changing when the height is 16. So one thing to be careful of is sometimes they give you too many numbers. And in this case, that 19 is not that it's too many, because we're still going to use it in one way, but it's not the height that we want to use to plug in at the very end when we plug in all our numbers. Okay, so based off of all the information here, do we want to find the surface area of the tank, the volume of the tank? Like, what do we want to be our starting equation?
We're looking for the rate at 16 feet, correct?
Uh-huh. And so like what equation do we want to start with? Like for 2R, we started with the Pythagorean theorem. So what formula do we want to start with for 12R?
Would it be the volume?
Yeah, it would be the volume. And
Okay.
so I think the context here is like they give me dV dt, which means they want me to have some sort of volume representation in this formula, okay? So we're gonna write the volume formula for not a cone, a cylinder, and that is pi r squared h, okay? Now, I know that pi is a constant, so when I take my derivative, I can pull the constant out to the front. So if I take the derivative of v, I'm going to get dv dt. Now, one thing that I think we did right off the bat with 2r is we said we know the length of the ladder, but we also know that the length of the ladder is not changing. And so we were able to say that equals 0. So if we go back to 12R, one thing I noticed is that the radius is 4 feet, but the radius of a cylinder, by definition, it doesn't change. So no matter how high the water is inside the tank, the radius will still be 4. So I can represent that like dr dt is 0. Okay, so things that don't change have a rate of change of 0. Now, why is that helpful? Well, when I look at this, remember, anything that's a constant, like it doesn't change ever in the entire problem, can be pulled out to the front. So pi can get pulled out to the front. R squared can also get pulled out to the front because the radius doesn't ever change. Now, if I had a cone, that would be a different story. But for a cylinder, the radius doesn't change. So really, the only thing I want to find the derivative of is h. And the derivative of h is dh dt. So it's actually a pretty straightforward derivative as long as you can identify what's constant, okay? And now that you have your formula, let's plug in all the numbers we have. So dv dt will be -1. I have pi 4 squared, and then I have dh dt. All right, well, it turns out that we didn't even need to plug in our 16 or our 19. All right. So again, sometimes you use all of the numbers like we did in 2R, and sometimes you don't use all of the numbers. All right, so let's solve for dh dt. So -1 equals 16 pi dh dt. So dh dt equals -1 over 16 pi. All right. So how are we doing out there in cyberspace?
Hard.
Doing good.
Okay. Do folks have questions on WebAssign?
Number 67.
Number 67 on the original assignment, right?
Correct.
Okay, 67. All right. Oh, funny, I was looking at this one earlier. Okay, so the integral of cosine pi over x to the, what numbers did you have as your power?
Let me see. Hold on. 23 and 24.
Okay, so 24 on the bottom, yeah, and 23 on the top.
Yeah.
Okay, cool. So let's take a look at this. I think this is actually another case where sometimes if we split it up or write it a little differently, it might help us determine what we need to substitute. So what I mean by that is cosine of, I'm going to change pi over x to the 23 to be pi times x to the -23. And then I have x to the 24 down here. And I'm going to make one more change, and that's going to be, I'm going to split this into two fractions. So cosine of pi x to the -23 times 1 over x to the 24 dx. So I think negative powers are always a little trickier to see. So what we're going to do here is I'm going to identify my u. So my u, again, is usually the thing raised to the power. However, if we're looking at trig stuff, it's usually the thing that is being cosigned or signed. So like a more simple case might be like a question where you have like cosine of 2x dx, like you would use u as your 2x there, okay? So this is the same, it's just a little bit more complicated looking, but we're gonna take this thing that's being cosigned and set it equal to u. So pi x to the -23. And from there, we're gonna find our du. So pi, bring down the power, and lose a power. So -23 minus 1 is 24. So I know that we're used to like seeing the one with a smaller power as our du, but in this case, because it's a negative number, it's going to get more negative, and that looks like a bigger number if it's on the bottom of the fraction, but it's not actually a bigger number. So if I rewrite this a little bit, I get du equals, let's see, -23 pi times 1 over x to the 24 dx. And so when I write it that way, I can see a little bit more clearly that 1 over 24 dx is 1 over 24 dx. And so what I need to move is I need to divide that negative 23 pi over to the other side. So I get negative 1 over 23 pi du equals 1 over x to the 24 dx. So if we come back to our equation and we make substitutions, we'll get the integral of cosine u times negative 1 over 23 pi du. Okay. I'm going to go ahead and pull out any constants to the front. So negative 1 over 23 pi, the integral of cosine u du. And I know that the integral of cosine is going to be sine u. And then I need a plus c because I don't have bound. And then my last step is to put back in my u. So I'm going to get negative 1 over 23 pi sine of pi over x to the 23 plus c. All right, does that clarify number 67?
Yes.
Yeah.
Helps.
Yeah. Okay, cool. All right. So how are folks doing? Are there other questions that you would like to go over from WebAssign? If you're feeling like you're good, you can certainly take off, no hurt feelings. But I want to make sure that this time is valuable to those folks who want to stick around.
I had a question on how to, so with the graphs where we use LRAM and RRAM, where we use the medium or median.
The middle one?
Yeah, the middle one. I just found it kind of like odd on a couple. I'm trying to find the one that uses that right now.
Okay.
Hold on, sorry.
No worries. I'll look too and see if I can find one on the exam review.
Oh, that would be cool.
Yeah.
I was able to figure it out, but I just wanted to see another example.
Yeah, I do think the MRAM is a little less counterintuitive for sure.
Can I ask a quick question about one of your steps here in 67?
Yeah, for sure. What's up?
Just so between or that goes from cosine of u to sine of u. If you could just explain real quick how
Oh,
you got
like how I went from here to here?
Mm-hmm.
So the sine and cosine is definitely should be on the list of like antiderivatives or integrals that you know. So like what function did you take the derivative of to end up with cosine? Like when you take a derivative and you end up with cosine as your answer, what was that?
Sine?
Yeah, that's where I got sine from.
Okay, gotcha.
Yeah.
Okay.
Okay. Let's actually.
It was number 20 on the WebAssign, but if there's one on the exam review, that would be great.
Yeah, let me just go back and see what we approximating area. Oh gosh. Okay, so let's actually take a look at this question. Okay, so this is from the 5.1 lecture, so there should be a video on it, but let's go through this question anyway, because I think a lot of people have that same question about like, how do you do that approximation? So having a table like this, we can see that our A value, our A value is 0, because that's like where we start taking the readings, and that at the very end, we stop after 30 seconds, okay? So when I think about LRAM, I want to break it up into 6 rectangles. That means that I'm going to need the first 6 Y values. So I would need this one, this one, this one, 1, 2, 3, 4, 5, 6. And when I think about my formula, I can say area equals, to find this, like, so all these numbers are the heights of the rectangle, but to find the width of the rectangle, I need to do B minus A over N. And so my B is 30 minus my A is 0, and I want a total of 6 rectangles. And then I'm gonna multiply that by 7 plus 21 plus all the way until I get to 31, and then I'm gonna stop. Okay. If I simplify that front fraction first, that means the width of every rectangle is gonna be 5. And then the heights of the rectangles are different. Okay. Does that setup make sense to folks?
Yes.
Yeah.
Yeah. Okay. So for our RAM, we still have our B minus A over N, but this time we're going to pick the last 6 values. So I'm going to start at 21, and I'm going to stop when I get to the end Y value. And my B and A are still the same, 30 minus A, and I still want 6 rectangles. Okay. Now, what if I said, I want you to find our RAM, but with 3 rectangles? How would that change our setup?
You'd put 3 on the bottom where N is.
Good, yeah. So I've got 30 minus 0. So B minus A is still the same, but this time I'm going to divide by 3 because I only want 3 rectangles. So that was something I noticed. So with some of the questions I've gotten about approximation is sometimes they change the number of rectangles on you and you're still finding the old number of rectangles. And so you end up with numbers that are like twice as big as what you should get. So just make sure you change that if the number of rectangles gets changed, okay? Now something else is going to change in this because I'm not going to use 6 Y values. In fact, I should only have 3 Y values.
The last 3?
It's actually not going to be the last 3, no.
Oh, or is it going to be the one after 17, 21, 24, 29?
No, it's not actually. So we're gonna use, so if I have 3 rectangles, how wide is each rectangle?
One. Wait, 3 rectangles. How wide is each?
By 1, do we mean 10?
Well,
Would it be twice as wide?
oh, got it. Okay, yeah, 10.
Yeah, so 30 minus
I
0.
see what you mean. Yeah, I see. I'm looking at
Okay,
the chart.
so
Okay.
the width of each rectangle is 10. Okay, so let's go back to our x values for a moment. That means my first rectangle starts at 0, and where does that first rectangle end?
At 10?
At 10, yeah.
Yeah.
So the first y value you're going to use is 24.
Okay.
Okay. So now the second rectangle, where does the second rectangle start?
The second rectangle would start at 10,
It would start at 10. Where does it end?
20,
So guess what your second y value is?
and 32.
32, yeah. And then my third rectangle starts at 20, finishes at 30. So I'm going to need to use the 28. Okay. So I'm glad we went over this because I think that sort of clarifies what happens when we don't have to use all of the values. And I think that might help with our let's find the MRAM. Okay. So MRAM with 3 rectangles. So area is going to be B, which is 30, minus A, which is 0, over 10. And if I'm stuck on which y values to use, let me just remind myself that every rectangle has a width of 10. So I know where the rectangles start and stop. In fact, they start and stop at the same place as RRAM.
30 over 3, right?
Yeah, yep. Mm-hmm. Okay, so let's go back up to our table. If I know that my first rectangle starts at 0 and ends at 10, what is the middle x value?
Gonna be 5, 21.
And so I would use 21 as the first height of the first rectangle. The second rectangle starts at 10 and finishes at 20. Halfway is 15, so my second y value is going to be 29. All right, and what's the last y value that we're going to use here?
31.
31, good, because the last rectangle starts at 20, finishes at 30, and halfway in between is going to be 25. So the corresponding y value is 31. Okay. Does that help clarify a little bit more, like how do we know when to use what values?
Yes, it does.
Okay,
Yes.
cool. Cool. All right. Are there any other questions? And again, it doesn't have to be from WebAssign. I love that people are asking like sort of global questions. But does anyone have any other concepts that they'd like to go over?
I'm just taking notes now. I'm just trying to just get practice of any different concepts that we're talking about in this session. So whatever
Okay.
anyone else has, I'm okay with.
All right, cool. Well, let me look back in WebAssign. All right.
Can we look at number 23? It's the same where you're solving for area, but it's with the graph and a little stuff.
Is that on the homework, number
Yeah.
23? Okay.
Yeah.
I'm sorry, did you say 23?
Yes.
Okay. All right. I do think 23 is maybe going to look different for everyone because it looks like it's a red graph. So I'll go ahead and draw what we have here. But I think in general, you're going to be using like trapezoid formulas, triangle formulas, and rectangle formulas, it looks like. Okay, so this is sort of what my graph looks like. And I think each one of these tick marks is 18. So 18, 36, 54, 72. And then this one looks to be 18, which would make this first one 9, and this would be 27. So on the bottom, I have negative 27, negative 18, and negative 9. Okay. So let's take a look at these questions. So the question that I have says the first part is the integral from 0 to 18 of f of x dx. And so one way that you kind of know you're supposed to use geometry is they don't even give you a formula for f of x. So that doesn't mean like, oh, I'm not going to give you a formula, so you have to come up with a formula. It means, especially when everything is like kind of nice and geometric, like they really want you to use area formulas. So if I were to kind of shade this in or outline this area that I'm finding is going to be like this area here. Does that make sense?
Yeah.
Okay. So what that means then is I need to find the area of a trapezoid. And it's sort of a trapezoid standing like on its height. So if I want to use the area formula, 1/2 base 1 plus base 2 times the height, I have to be careful about which values I use. So base 1 is actually this part here. It's like the first standing up part. So I know that that has a y value of 9. Plus base 2 is like this part, and I know that's 27. And the height is this part, which is 18. And so once I have all my numbers, it's just a matter of number crunching. So, and 18 times 18 is 324. All right. Does that clarify the first one?
Yeah. Could you technically solve it too by breaking it up into a triangle and then a rectangle? Or is that just extra?
Yes, you could. You could. Mhm.
Okay.
All right. So let's go ahead and take a look at part B. So part B for me is the integral from 0 to 45 of f of x dx. So in addition to the orange area that I have, I'm also going to be adding on this area. So what I can do is I can take my 324 from before and just use the trapezoid formula again to find the red part. So I could have 1/2 base 1 plus base 2 times height. And that equals 324 plus 1/2. Now this trapezoid is more like a regular trapezoid. So like I would say that base 1 would be like down here and base 2 would be like up here. So base 1 looks to be 45 minus 18 is going to give me 27. And base 2, it looks like it's going to be 9 times the height, which is 27. And so when I type that all in, I should get an area of 810. Now, the last two that they ask for, part C for me says go from 45 to 63 of f of x dx. So if I look at my diagram from 45 to 63 is going to be like a triangle right there, that green triangle. And so I can just use my area of a triangle formula, which is 1/2 base times height. So I get 1/2, and my base, it looks like it is 18. And the height of that triangle goes down to -27. So this is 9. 9 times -27 is -243. Okay. All right. And the last part says to go from 0 all the way to 81. So 81 is like right here. So I could just take the areas that I already found and then just subtract this one last area, which is this trapezoid right at the end. Okay? So let's find the area of that blue trapezoid. So that blue trapezoid has an area of 1/2. I'm going to say that this is base 1 and this is base 2. So -27 plus a -18 times a height, and I'd say this is the height, so that is 18. And when I evaluate that, I'm going to get 9 times, and I get -405 for the blue part. Okay, so to answer the last question, part D, I'm going to take my answer from, I'm going to take the orange one, and I'm going to add the red one, and I'm going to subtract the green one, and I'm going to subtract the blue one. And when I do all of that, I think that gives me an overall area in part D for 162. So that's just if I add the things that are above the x-axis and I subtract the things that are below the x-axis.
You subtract it as a minus, or do they?
No, you either add it as a minus or you subtract it.
Okay.
Yeah, that's a great question though.
Thank you.
You're welcome. Anybody else have any other questions that they'd like to see, or are we ready to go kind of study on our own? Where are we at here, folks?
So I just had a quick question on this one, actually. So I understand how you're setting it up and everything. I guess what's confusing me is just how you're getting the height, just because, you know, they're trapezoids instead of just normal triangles or rectangles.
Okay, so let me draw sort of the two common orientations of a trapezoid, okay?
Okay.
So if you're looking at trapezoids, when we think about them from grade school, we tend to think like we have something like this, and then like this, right? That's what we tend to think of when we think of a trapezoid. And we have like our base 1 and our base 2 and then our height. But it's kind of like somehow we all just got in the habit of drawing equilateral triangles. Like if I asked everyone to draw a triangle right now, I bet we would all draw ones that are like equal on all sides. And I don't know why that is, but I think it's just kind of like how we got to, you know, learning those. So one thing that I would sort of encourage you to think about is most of these trapezoids are either going to be like, let me see. Most of these are actually going to be right trapezoids. And what I mean by that is it's like this, and like this, and then like this, and then like this.
Yeah, they have a right angle.
Yeah, so this is my height, and this is my base 1, and this is my base 2, okay? So it's sort of like a modification. What's nice about this is it's really easy to count the height because you can just count how many boxes are on the grid.
Okay.
But what we also do is sometimes we turn our trapezoid, we rotate it like 90 degrees. So sometimes our trapezoids look like this. So all I've done is rotate.
Got it.
And so in this case, all the sides rotate as well. So like this, even though it's standing up and down, is my base 1.
Gotcha. Okay.
And this is my base 2, because the definition of height is not that it goes up and down, but the definition of height is that it's perpendicular to both bases.
Okay.
Okay, so then this is my height because it's perpendicular and perpendicular. And this one is perpendicular and perpendicular.
Okay. Yeah. Okay. See, I understand now. Okay. Yeah. I see. Simple stuff there. I was just confused about it a little bit.
Yeah. No, that's totally valid. I feel like, especially like trapezoid, like when they teach it in elementary school or middle school, they're like, well, here's this fancy new formula, but you can always do like just a triangle and a rectangle, which is fair. But I think in the middle of a problem, it's kind of a lot to break everything down into like rectangles and triangles. So if you can see the trapezoid, it does make the work a little bit faster.
Okay.
Yeah. Okay.
Thank you.
All right. What other questions, folks? These are super, super good questions, by the way.
Can we take a look at 39?
Yes, sir. Okay. So 39. I think the function is the same. It's like cosecant t cotangent t dt. What are your bounds?
Sorry, pi over 4 to pi over 3.
Oh, okay, same as mine. Pi over 4 to pi over 3. Okay. So this is one that also looks maybe more complicated than it is. And what I mean by that is, let's think about what we know about derivatives, okay? So I know that if I take the derivative of sine x, I get cosine x. But what that means for me is that if I integrate cosine x dx, I get sine x. And if I take the derivative of cosine x, I get negative sine x. And that means if I integrate sine x dx, I get a negative cosine x. And you can do this for all of the trig ones, but let's skip to the one that maybe is more relevant in this case. So if I take the derivative of cosecant x, I get negative cosecant x cotangent x. So what that means is if I integrate cosecant x cotangent x dx, I end up with negative cosecant x. And so that's useful for me here because I know that this cosecant t cotangent t is like this.
Oh.
And so I don't need to use u sub. It's not anything like that. It just happens to be one of the common integrals. So my integral here is going to be negative cosecant t. And I'm going to plug in pi over 3, and I'm going to plug in pi over 4. And so when I do that, I get negative cosecant of pi over 3 minus negative cosecant pi over 4. Now I'm going to use what I know about reciprocal functions. So I know that cosecant is 1 over sine. So that means I can write this as 1 over sine pi over 3. And then I'm going to combine those two to make a plus. And I'll do the same thing with the cosecant pi over 4. It'll be 1 over sine pi over 4. And now I'm going to go back to my unit circle for some values. So 1 over sine of pi over 3 is root 3 over 2 plus sine of pi over 2 is root 2 over 2. And I'm just going to use the definition of a reciprocal. So like 1 over anything means the reciprocal. So the reciprocal of root 3 over 2 is 2 over root 3. So I've got a negative 2 over root 3. And then in the second part, 1 over root 2 over 2 means the reciprocal of root 2 over 2, which is 2 over root 2. Now, just to make sure your answer gets accepted by WebAssign, like this is totally fine for like an exam. I noticed that WebAssign reduces the second fraction a little bit more. And so they keep the first fraction the way it is. They don't rationalize that denominator. Plus, let's take this denominator and keep it. But another way of writing 2 is the square root of 2 times the square root of 2. which is nice because then I can reduce one from each, and I end up with -2 over √3 plus √2.
Awesome. Thank you.
Mm-hmm.
I have a question about this one.
Okay.
Yeah, because my bottom number is pi over 6. And
Mhm.
when I was looking at the unit circle, I just didn't know like what number I should use. If I should use like √3 over 2 or 1 over 2.
So if you're looking for the sign value, sign is the y value on the unit circle.
Okay, just making sure. Thank you.
Mm-hmm. All right. Any other questions, folks?
42 or 43. Yeah, 43 with the inverse tan on the WebAssign.
Okay. Okay, cool. Yeah. All right. Well, let's do 43. Okay. So 43, mine says the integral from 0 to 1. What is your number on the top?
It's 8.
8. Okay. So 8. All right. So in this case, really good identification that you need inverse tan. One thing I can do is I can take the 8 out to the front right away. So I can see maybe a little bit more clearly that I have 1 over t squared plus 1, or 1 over x squared plus 1. And so when I see something like this, this is a solid case for inverse tangent, okay? But just to kind of set the stage for Calc 2, if I changed it a little bit and I did like t over t squared plus 1 dt, this is a really solid case for u sub, okay? So just so you kind of don't always think that if you have t squared plus 1 on the bottom, it's going to be arctan. It could be u sub depending on what the numerator is. Okay. But to answer your question, we're going to take 8, which is my constant. I know that when I plug it into the formula, that I end up with arctan of t. And then I'm going to plug in 1, and I'm going to plug in 0. And so I'm going to have 8, the arctan of 1, minus the arctan of 0. And I have 8. And I'm actually going to write out in words what I'm looking for. So when I see arctan of 1, I'm looking for an angle with y divided by x equal to 1. And that angle has to be between -pi over 2 and pi over 2. Okay. And then I'm going to subtract. When I see arctan of 0, I'm looking for the angle with y over x equals 0. And again, I want to pick from -pi over 2 to pi over 2. So this is the same thing as saying this. And arctan of 0 is the same thing as saying the angle with a y over x of 0, but I have to pick between -pi over 2 and pi over 2. All right, so if you go to your unit circle and you're trying to find an angle where the y divided by x gives you 1, then that means that your y and your x are actually the same number. Because if I have something on the top and it's the same as something on the bottom, then I can go ahead and reduce that to 1. So the angle where I have that happen is pi over 4. Pi over 4 has an x value of root 2 over 2 and a y value of root 2 over 2. Minus, if I'm looking for an angle with a y over x of 0, the place where that happens is actually at, where is that? Y over x is 0. That's going to be right here, because the y value is 0 and the x value is 1. So if I take 0 and I divide it by 1, I get 0. And so this angle is actually going to be 0. And so when I go back here, I end up with 8 times just pi over 4, which is going to give me 8 pi over 4, which is going to give me 2 pi.
Yeah, that's perfect. I was just trying to find the angle.
Yeah,
with
that inverse
understand.
trig, man, it's tricky, it's tricky.
So yeah, that makes much more sense. Thank you.
Yeah, and this is actually a really good example if you're like, oh, I don't know what to put on my cheat sheet, like writing it out in words, what you're looking for, I think is so, so useful. Because I mean, even when I'm taking my own math courses, I'm like, I forget what that symbol means. Like I have to write it out so I know what it means. And the more I document when I do like my homework and stuff, the easier it is for me when I get to a test, because I already kind of built in that like, okay, I know this symbol means that, I know where to find that.
Yeah, exactly. It works.
So
All right.
you know where you circled it in the orange?
Yeah.
So if you were to just take 0 and 1 and plug them in for t, that would be wrong.
That would, yes, that would be incorrect.
Okay.
Okay. And the reason why is I think you're maybe confusing that. Like if I have an integral and I have bounds, like whatever my function is, I have to find the antiderivative.
Right.
Or I have to find the integral.
Yeah.
But that's different from what we saw earlier where we had d dx, the integral, with bounds, and f of t dt. Okay, because this case is where you end up with some form of your original function.
Yes. Okay.
Yeah, that's a really good clarification, actually. So antiderivative, if you don't have like a ddx anywhere in there, or if it doesn't say take the derivative, you actually have to do something to it before you plug in the numbers. And then if it says find the derivative of the antiderivative, then you know you can just kind of plug in bounds. All right, we got about 15 minutes left. Folks have more questions?
Ali said number 80.
80. All right, thank you.
The microphoneless man.
All right, number 80. Okay, the integral of dx over, what are his numbers?
25 and 16.
Like this?
Yep.
Okay, cool. All right, so I'm gonna do one thing that I've been doing, which is move the dx to like the end, and that'll keep my numerators of 1. So 1 times, and I'm even gonna do this, 5 squared plus 4 squared x squared. 4x squared. Okay, so the arctan formula says that you're going to, if you want to take the arctan of, no, sorry. You have the integral of 1 over u squared plus a squared du, then what do we get with that? What is that formula?
It's like 1 over a inverse tan u over a or a over u? Yeah.
Is it u over a or a over u?
Let me look. It's u over a.
U over a. Okay. Yeah, because our x at the end should be like on the bottom.
Yeah.
Okay. So when we go ahead and figure out our values, we'll get u is not 25, but it's going to be 5. And a is not x, but it's going to be 4x. Okay, so that's kind of why I split like this 25. I wrote it as 5 squared, so it'd be easy for me to find my u. Actually, sorry, that's not the u. That is our a. Okay, so 16x squared gives us 4x in parentheses squared. That gives us our, oh my God, Judy. That gives us our u squared. All right, so u will equal 4x. And then our 25 is really 5 squared, or that gives us our a squared. And so a equals 5. All right, so let's plug everything into our formula and kind of see what we get. And we're gonna get 1 over a is 5, the inverse tan of u, which is 4x over our 5. Okay. Is this what you are getting as your answer, Ali? And I'm going to guess that's a no, okay?
He said yes, but it's still wrong.
Okay, so what we need to do here is we also need to include the fact that like our u is not just x squared. So we have a 4x in here. And so this is a case where we also need to say du equals 4 dx. But I'm going to need to divide that 4 to the other side. So really, I have an additional factor of 1 over 4 that I need to consider. So if we do that, then I think, Ali, you should get 1 over 20, and then inverse tan of 4x over 5. And that should be correct.
Said it worked.
All right, cool. So if folks are working on number 20 for themselves, let's just make sure that we highlight this part. There's going to be an additional factor for your use of, okay? All right. Anyone have any last questions?
Just quick question. This is also going to be uploaded, right? This whole recording?
Yeah.
Cool. On YouTube, or is it going to be on Canvas?
The link will be on Canvas, but it will be housed in YouTube. So if you subscribe to the YouTube channel, then it should pop up whenever it gets uploaded.
All right, cool.
Okay. All right, well, I'm gonna come back into the room then. Alrighty, folks. So I hope this has been helpful in terms of a review. I feel like folks asked really good questions. Don't forget that Danny has his peer mentor sessions today from 4 to 6, and the list of topics that he's going to cover is in this week's announcements. And then he was also able to move his regular Thursday peer mentor sessions to Wednesday to give you guys a little bit of extra support before the exam, okay? The exam is going to open at 9:35 on Thursday morning. I will be on Zoom for a little bit just as people get started. So if you have any questions, you can come into the Zoom room and ask. But other than that, I'm just going to remind you the cheat sheet for this one, you actually get 2 sides of a piece of paper. So I know that we're learning more and more new stuff, and that we're realizing maybe there's stuff we learned in other courses that aren't quite as fresh. So if you feel like you need a little bit more room, definitely do so. My biggest reason for saying, yeah, let's do a cheat sheet is because I think it is a valuable experience to learn how to make one and how to make one that actually serves you well on the exam, okay? And so I want to give you that kind of practice with crafting a cheat sheet that works for you, okay? Don't just like write down 3 random formulas and call it a day. Like, take the time to actually do it. And if you feel like, you know, you really want to challenge yourself, you're welcome to write your cheat sheet and not use it on the test, but make sure that you include it with your submission. Okay, so when you turn in your test, it's going to be due on Friday morning at 9:35, so you have 24 hours. When you turn that in, you need to have your cheat sheet. You need to have your handwritten and signed statement of integrity, and you need to have your exam, okay? Please make sure that things are in order. It's easy for me to find. Not so much with this class, but with one of my other classes, it was really hard to read some folks' work, and it's hard for me to kind of chase people down. So if you have work that's submitted that's not legible or the quality is not super clear, then you're not going to get points for any potential work, okay? Make sure that you get everything in by 9:35 on Friday morning. So if you don't turn it in the night before and you wake up at 10 a.m., that's tough. But I really want to support you here. So, you know, we have the 24 hours, but you kind of need to make sure that you have everything submitted. I will not be taking late submissions via email, so make sure you know how to make the technology work. And if you want, you can hang around the Zoom room. I'm happy to show you, you know, the technology again and make sure that you feel comfortable with it. But if I don't hear from you, then I assume that you are all good to go. I think that's it in terms of announcements on my end. Does anyone have any questions before we all take off?
Yeah, so do you recommend, I use Notability on my iPad.
Mhm.
Do you recommend transferring the test to Notability and then doing it? Or do you recommend just printing it out?
Whatever works for you. If you're fine doing your work on a tablet, then yeah, you can just download the PDF of the exam, import it to Notability, and do your work right on it. That would be fine.
Okay.
Mhm.
Got it. Thanks.
Yeah. Thank you. Any other questions?
What app do you suggest? Because for the last exam, I was having trouble. I looked through like 4 different apps to try and compress all the pictures into one PDF file,
Okay.
and that's why I was having so much trouble with it.
Yeah,
last
yeah.
time.
No, it's stressful. I know.
Yeah. So then you know what happened. I emailed you about
Yeah.
it, but
Okay.
do you
So-
have maybe it's different for Apple products because I have an Android, but I mean I don't know if maybe there's an app you suggest or something.
Okay. So let me just share my screen real quick. So if I go into Canvas, and I go to the home page under logistics,
Mm-hmm.
the last thing says how to take and submit an exam.
Gotcha.
So if you click on that, it should tell you how to take the exam and then to submit the exam. So the apps that I have used are either Genius Scan
Mm-hmm.
or Tiny Scanner.
Got it. Okay.
And I think that they should work for iPhones and Androids. I tried to pick apps that work for both. I've seen some other people use CamScan,
Mm-hmm.
Cam Scanner.
I use Tiny Scanner and I've been using it forever, so it works great.
Okay.
And I have Android too. That's why I meant to say that.
Sweet.
Okay.
Yeah.
Yeah, so if the Tiny Scanner, it looks like a tiny scanner. Like, it's so cute. And then the orange one is the Genius Scan, but I've been using that one only because I can airdrop stuff to myself. So if you're using an Android, that's probably not very helpful for you. But I did find Tiny Scanner also useful. So thank you, Alexis.
Okay, cool.
Yeah.
Google also has an extension. It's called Mergy, and then that works for every device, and then you can just compress it into one file and then just upload that.
All right. Any other questions, folks? All righty. Well, we'll call it a day here. There are peer mentor sessions today and tomorrow, so you have a lot of options for support if you want between now and Thursday's exam, okay? So study well, good luck, and I look forward to getting your tests on Friday morning.
Thank you,
All right.
Professor.
Thank you so much.
All right, bye folks, see you
Really appreciate
later.
it. Bye.
Good one.
See you later.